All right, can y'all hear me okay? Okay. So we finished off discussing time dilation. This effect that we talked about when we left was called time dilation. So now I'm going to talk about another effect. The second effect I want to talk about is length contraction. Okay. So let's go back. I mean, we're going to use the fact that we have time dilation. Let's assume that when the rocket observes those two flashes, we measure that the rocket travels a distance L naught. Okay? And they're denoted by the two coordinates y1 and y2. The distance between y1 and y2 is L naught. And we say that that rocket traveled that distance in some time t, or delta t, let's say. What does the person in the rocket observe? So we observe, let me get another marker, sorry. So we observe the rocket travel a distance as the observer on the rocket emits and receives a signal. So to us, that distance, L naught, is going to be the speed of the rocket times delta t. But that's not the case to the rocket. The person in the rocket will measure a different distance. Because why? Because this time is different. The person in the rocket will measure the distance from y1 to y2 in time t delta t prime. And so that person measures the time. L is equal to v delta t prime. But delta t prime is delta t over gamma. Let me go down here. So L is V delta T over gamma, which is L naught over gamma. And since gamma is bigger than 1, that means that the person in the rocket says the distance between y2 and y1 is less than L naught. That distance is contracted. Okay? So if we move by an object, let's say a ruler, if we zip by a ruler, that's 1 meter, the meter will actually appear shorter to us. We will actually, and I'm using the word appear, that's not right. We would measure the meter to be shorter than a meter. Okay? So if I had a meter stick, if I was in a rocket and I had a meter stick, and I went by and I measured the length of this meter stick somehow, it would be shorter. I'm not sure I understand your question, Jacob, because if this is the equation for delta t, isn't that true? And the person in the rocket measures time delta t prime. Okay.
But wait, on the one screen you have delta t is delta t prime gamma. On the other screen you have delta t prime is delta t gamma. For both of those to be true, when one of the primes have to be switched. Oh, it's divided. Okay, never mind.
Yeah, it's divided.
Sorry.
Yeah, try to make it clear. Okay. Any other questions? Okay, so that's the implication of Einstein's second postulate. And it does, his postulate, you know, the implications actually we observe. Now, so lengths of objects are shorter when measured in a moving frame. The length of an object measured in a frame in which the object is at rest is called a proper length. In other words, when you measure the length of an object, you're measuring, you're locating its endpoints at the same time. You really can't do that when you're moving. Okay? So the proper length is, we define the proper length as when you measure the location of the endpoints of the object at the same time. Lorenz and Fitzgerald, they originated the idea to explain the null effect of the Michelson-Morley experiment, but then it was disproved later. So the idea of length contraction really came from Lorenz, but they used it for a different reason. That's why it's called Lorenz contraction. So what I want to do is an example, or discuss an example where we observe time dilation, a real life example. Okay? Because people don't believe it. They think it's, you know, it's only in theory, whatever that means. Okay. And in physics, theories, when you use it, when you develop a theory, there's some experimental verification behind it, okay? So, let me rewrite my equations. Okay, so I want to just discuss a real-life example of time dilation. So there's these particles that actually enter the Earth's atmosphere and travel to the Earth. They're called muons. And muons are produced from the decay of other particles, and they really come from cosmic radiation. They come from outer space. And these muons decay. They're not stable. The pion decays and you get muons, and the muons decay and you get other particles. Okay? And they decay. If you've had radioactivity, maybe if in chemistry you've talked about radioactivity, I don't know if you had a chemistry class, but when you talk about radioactivity, when something is radioactive or something decays, it decays according to the following equation. The number you have at any time is equal to whatever you started with times some exponential decay factor. Okay? So particles decay exponentially whether they're when they're radioactive, for example, and they decay according to that equation. This represents how much you started with, and this represents how much you have at some time t. Okay? And we want to look at these particles called muons. That are in the upper atmosphere. They're produced from secondary radiation when another exotic particle called a pion decays. The pion decays, gives you a muon. The muon decays, it gives you other particles like electrons, etc. Okay, so as they travel towards the Earth, if you have a bunch of them at the top of the atmosphere, as they travel down towards the Earth, you're going to get less and less of them, because in the time it takes for them to get from the top of the atmosphere to our Earth, they go through a decay process. Okay? So because of the time it takes to go from a certain distance from above the Earth to the surface of the Earth, you're going to measure less just because of the fact that they decay into other particles. Now, the lifetime of these muons is about 2 microseconds. If you do an experiment, let's say the muons are 9,000 meters above the Earth. So suppose you have 10 to the 8th muons at a location of 9,000 meters above Earth's surface. And these suckers move fast, okay? They move at this is not going to be the exact number. I'm just going to give you a value. Let's say they move at a speed of 0.998 times the speed of light. Okay, so these things are moving very fast. They're moving close to the speed of light in their atmosphere. Okay. How long does it take for these particles to get to the Earth? All right. How long does it take for them to travel 9,000 meters? Well, I just take distance over time, right? I do t, and I'll call it a time interval. Delta t is equal to 9,000 meters over 0.998 times the speed of light. That time interval that we would get is 30 microseconds. Okay? So how many do I have left? How many do I have left after 30 microseconds? If I had a detector on Earth, if I had somebody who said there's 10 to the 8th muons 9,000 meters above the Earth, and then there's someone on the surface of the Earth detecting them, how many would I detect? Because they're decaying according to this equation. By the way, this tau is the lifetime of 2 microseconds. How many would I detect on Earth based on that equation? Well, I would put down 10 to the 8th times e to the minus 30 microseconds over 2 microseconds a lifetime. Well, when they reach the Earth, I would measure about 30 muons. So if there were this many at 9,000 meters above the Earth, and I had a detector, a way of detecting them on the surface of the Earth, in the time they travel from here to the surface of the Earth, I should only detect 30 because they decay. They decay really fast. They're only around for 2 microseconds. That's what I expect. But guess what? I don't get that number. In reality, one measures something around 3.7 times 10 to the 7th muons. The question is, why is that? Why would I measure this many if the theory says I only have 30? I should only get 30. I mean, that's a huge difference. Why would you think that? And it can be explained 2 different ways. Okay? It's 3.7. Sorry, I'll make the dot bigger. It can't be 37 because then it would be more than what I started with. Well, this delta t is 30 seconds in our frame. What is delta t? What is this time interval for the muons? Well, I got to calculate this. Now, what's gamma in this case? I chose these because because it becomes a nice number. It's approximately equal to 15. So gamma is about 15. So according to the muons, delta t is 30 divided by 15. What is 30 divided by 15?
2.
2. So according to the muon, only 2 microseconds have elapsed. So according to the muon then, then what I have left with is going to be 10 to the 8th times e to the minus 2 over 2, which is 3.7 times 10 to the 7th. Now, these are not the exact numbers from the experiment. I made up these numbers just for simplicity. But the experiment that was done by Rossi, it was like 1941. Rossi did the experiment in 1941. it showed this effect, that in the muon's frame, the elapsed time was much less than in our frame. And so they last longer than what you would expect. And so you would actually count this value. Because in the muon's frame, the clock runs slower. Okay? Now you can look at this another way though. Because to us, that distance was 9,000 meters, but that distance to the muon is not 9,000 meters. That distance to the muon is going to be 9,000 divided by 15, which is 600 meters, which takes 2 microseconds for it to travel. And you get the result. So this provides evidence for time dilation. Because, you know, people don't believe this stuff, right? And granted, it's hard to measure. In fact, an experiment was carried out with an airplane. So they used the most accurate clocks in the world, cesium clocks. They put a cesium clock on Earth, cesium clock in an airplane. They flew the airplane for 24 hours. And they calculated what the time difference should be between the two planes. Now, it's a very difficult calculation because you also have to take into account the fact that the airplane is accelerating. You have to take into account general relativity too, okay? But if you do a theoretical calculation for the difference in times between the clocks, and you look at the measured value between the time difference in the two clocks, they pretty much agree. This experiment, I think, was done in the 70s. Again, showing that there's such a thing as time dilation. Now, granted, the effect is small because the airplane doesn't go very fast. The airplane's going 500 miles per hour. Speed of light's 300 million meters per second. Okay. Questions on that? Does this seem bizarre to you? Okay. So let's look at another example. Let's do actually a simple calculation. Suppose you have astronauts in a spaceship traveling at 60% of the speed of light past the Earth. And they sign off from space control saying that they are going back to take a nap for 1 hour, and they call back. How long does the nap last as measured on Earth? So we're on Earth. Spaceship goes by us at 0.6 C. And they say they're going to take a nap for 1 hour. They're the moving frame, which means that their 1 hour is T prime. So how much time elapses according to us? Because we're the stationary. They're moving relative to us. Okay. So we're going to use the equation delta t equals gamma delta t prime. We're given that delta t prime is 1 hour. We're given that v is 0.6 times the speed of light. Notice I don't write 0.6 times 3 times 10 to the 8th because I'm being lazy. I don't want to write that out. And it's convenient to write it that way because when I do this calculation, the C's cancel. That makes life easy for me. So 1 minus 0.6, Squared, 1 minus, it's what? 1 minus 0.6 squared is 1 minus 0.36, which is 0.64. The square root of 0.64 is 0.8. 1 over 0.8 is the same thing as 1 over 4/5, which is 5/4. That's it. Questions on that? Remember that in our equation, the prime frame is also always moving. It's always the one that's considered moving. Okay. So here's a question for you guys. So two people of the same height pass each other in different elevators. According to relativity, what do they conclude about each other's heights? Anybody want to venture to guess?
Do they both assume the other one is taller?
Well, I mean, part of your answer is correct. Not taller. They're going to be
Shorter.
Shorter. They're both going to say the other person is shorter. Are they correct?
No.
No, they are correct, because that's what they measure. I mean, that's actually what they're going to measure. They're going to measure that person being shorter. It's only in your own reference frame, because you're measuring the proper length, that you're correct. But everybody else who's moving at the same speed relative to you is going to say you're shorter. Everybody. That's what they measure. And it's weird. I know. I understand. The thing is everything's relative now. Everything. Time intervals. That's what makes people feel uncomfortable about this, because how is that possible? Part of the problem is you're not measuring. If I measure my height and somebody goes by me, they're going to measure the locations of the ends of my body at different times. And so they're going to get a different value. This is not something that appears to be true. This is something somebody would actually measure. Now here's another interesting thing. This is another one that drives people crazy. If you see two events happen at the same time, normally you would assume that everybody would agree with that. But that's not true anymore. Simultaneity is not absolute. Okay? The fact that if you observe two events at the same time, somebody else that's moving by you will say they didn't occur at the same time. And the reason why is because you can't synchronize. You can only synchronize clocks in one frame. Everybody that's moving with you will say your clocks are synchronized, but not everybody else. Again, this is weird and hard to get used to. Two events are simultaneous in one reference frame if light signals from two events reach an observer halfway between the two events at the same time. And that's one of the ways we can synchronize clocks. So in other words, let's say I'm in a railroad car. Okay. And I'm standing right in the middle. Center light beam this way, and then center light beam that way. if those beams arrive at me at the same time, these two clocks that sent the signal are said to be synchronized. Okay? But somebody who's moving by will say they're not. Because the speed of light is the same in all reference frames. Questions before I go on? And there's different ways to view this. And so I'm trying to make, I actually have two viewpoints in your PowerPoint notes. I'm only going to go through one of them. And I'm going to try to send you a third viewpoint based out of that book I referenced earlier today. It's hard to get used to this idea. Imagine the following. And this is something Einstein thought of. Imagine there's a platform. In that figure, the platform is denoted by B, O, and F. Okay? O is an observer in between B and F. And a railroad car goes by you. Okay? A railroad car goes by you. Let's pretend you're at point O. And at the instant B prime, oops, there's a problem there. Let me fix that for a second. Hold on. Give me a second. I'll fix the other one later. Okay. At the instant B prime and B coincide and F prime and F coincide, lightning strikes. The lightning bolt makes a mark both on the platform and on the railroad car. Okay? So you're observer O, and you see lightning strike when point B prime and B coincide with F prime and F. And it leaves a mark. Okay, so far? So O prime sees the event happen at the same time. But what about the other person? O sees the event occur at the same time. But what about this person?
They see F first because they're moving in that direction?
Correct. So even though O sees the event at the same time, O prime will not, because the light from F prime will reach O prime first because he's moving in that direction. He or she's moving in that direction. So the events are not simultaneous in both frames. Oops. Okay. So I'm going to kind of show you the slides here because it's a little bit more difficult to draw these on the board. So what should we consider now? First of all, observer O says that the distance between B and F is L naught. Okay? But it's not the proper length of the train because the train was moving when the lightning struck between points B and F. Okay? What we want to do is calculate the time it takes for the light from the front of the train to reach O prime. And then we want to do the same thing. We want to calculate the amount of time it takes for the light from the back of the train to reach O prime. Okay? So I'll write it on the board. Because we want to find the delay time between the two events. So our goal is to find the time it takes for the beam, light beam, I guess, the light wave beam, however you want to call it, and I'm writing it down because I want to be careful, make sure you understand what we're doing here. And the time it takes for the beam from back of train to reach observer. The difference in those two values gives me the delay time between the two. It tells me how much the clocks are unsynchronized. Right? The clocks in our frame are synchronized, but what about the other person's frame? So in order to do the first thing, we need to realize that the beam reaches O prime when the position of the beam equals the position of O prime. So O prime is moving to the right at V. So XO prime then is equal to, if XO prime was originally at the origin, is equal to V times T. The position of the beam of light, starts here and moves this way. So if this whole distance, according to the person that are in train, is L, B prime, F prime, then this distance is half the value. So the position of the beam, the light, is going to be L, B prime, F prime over 2 minus the speed of light times T. Because if this is the origin, this beam is going towards the origin. So we set them equal to each other. You set them equal to each other at the time when the light from the front beam hits O prime. And I'm going to skip the algebra. And you get TF prime, which I lost a prime there in the notes, is L prime over C plus V. Oops, went backwards. Now we do the same thing again for the back of the train. Now for the back of the train, we want to find the time it takes for the beam to reach observer O prime. Okay. And again, we use the same idea. The only difference is my equations look different. When the light beam from B reaches O prime, then the position of the beam equals the position of the observer. So for the second part, we say that XO prime is just V times T. And X beam, since the beam starts on this side, if this is the origin, then this is negative half of LB over. But the light's traveling in the positive X direction. So at the time where these two coincide is when the observer measures the light, and so we set these equal to each other. And again, I'm going to skip the algebra, okay? And you get T sub B prime. Let me know if you can't see it. I'm too low. Okay? Now, if you take the difference, what do you get?
Is the prime on the T or the?
Oh, I should use V prime, sorry. That's been my mistake with my notation. I apologize.
Okay.
Now you take the difference, and you'll get this. If you factor out a C squared, and I notice I have a lot of notation issues. I apologize. But what is 1 over this thing? That's just gamma squared. Are we okay so far? This is the time difference between the wave hitting the front and the back of the train, according to O prime. Let me make this big real quick so you can see it better. But the distance between B and F is contracted according to O prime. Okay. So L naught, but, oops, sorry. L naught equals gamma times L sub B prime F prime. So we got to put a gamma in there. So what happens to one of the gammas? They cancel.
Okay.
And so the time delay that the O prime measures, sorry, I run out of space here. I'm going to have to erase this. The time delay that measures, or she measures, doesn't matter. Is going to be V L naught C squared gamma. Oh, I made a oops, I made a mistake here, sorry. The gamma squared was here. I made a mistake here somewhere, sorry. Okay. This is the time as measured by the observer in the train. So the observer in the train is saying, wait a minute, your clocks are not synchronized because I measure the clocks to be synchronized by this much. And since your clocks run slower, then your clocks are unsynchronized by the following. And in fact, since the clock, since the wave reaches the front of since the wave from the front of the train reaches O prime first, then the clock in the front is ahead of the clock in the back by this much. Okay? The clock in the front of the train is ahead of the clock in the back of the train by this much. Because the wave came from the front of the train first. So if you start the clock, then this clock will read this, the front clock will reach this much more than the back clock. Okay? It says that if B and F's clocks are synchronized, the ones on the observer in the train is going to say, no, they're not. They're off by this much. Because the events aren't simultaneous. Questions? Everybody's real quiet. No questions? Is it weird stuff?
Yep.
It is. I understand. I'm going to try to send you a different version of this. And the more versions you see, the better. In your notes, I have a different way of explaining it, so you can take a look at that too. So when two synchronized clocks move past you, the trailing clock leads by that amount. So this is something that's confusing to students. The trailing clock leads. What does that mean? What is the trailing clock in this example? Well, if you're the observer on the train, then the trailing clock is the one at location F. I mean, put yourself in the train. If you're moving to the right, B is in the front, F is in the back. F is the trailing one. If you're moving to the right. Okay, that always confuses people. The trailing clock, the trailing clock that moves past you is the one that leads by that amount. So from a different point of view, if I'm standing here and I have a railroad car with two clocks moving this way, this is the one in the back as they go by. So that's the trailing clock. So that one's going to lead this one. But in our example, the observer O prime is observing the supposedly synchronized clocks on the platform. And so F is the trailing clock.
It's because you're moving, or B is moving towards where you were, kind of, right?
Yes.
And F is moving away.
Yes. And so I have the different point of view. You can look at it. I'm going to skip that here, just in the interest of time. So let's do an example of this weird stuff. Okay, I'm gonna keep focusing on this light clock example because if you use the same example the whole time, maybe that the stuff will become clearer. So let's say we have that same light clock. Let's put some numbers in. Okay, there's the rocket. A lot of times these things are called light clocks. Let's let D equals 15 light seconds. Okay, what does that mean? Can anybody tell me what 15 light seconds mean?
How far light moves in a second?
Yeah, it's just how far light moves in a
many.
second. It's the speed of light times time, okay? Because otherwise you got to write 3 times 10 to the 8th. We're trying to do things shorthanded. Let's assume that the speed of the craft is 80% of the speed of light. Okay? So light beam goes from here to here and back. What's the time interval? So the person, the observer on the platform, sees the light go from here to here and back in 30 seconds. Okay, it's a big spaceship, all right? Okay, so the light goes back and forth in 30 seconds. If we're on the ground observing this, that's the bottom figure, how long is that? What is delta t? Well, delta t is going to be delta t prime over gamma. Well, what is gamma in this case? Gamma is going to be 1 over the square root of 1 minus 0.8 c over c squared. Oops, that's a minus sign. And this comes out to about 5/3. Okay. Oops, that's wrong. So that ends up being 30 seconds times 5/3 equals 50 seconds. And that agrees with the time dilation stuff we were talking about before. So it takes 50 seconds for the light wave to us to go from here to here and back, as you see in the bottom picture. How far does the rocket travel? According to us. Well, it's going to be 50 seconds times 0.8 c, which is going to be 40 light seconds. Or 40 times c seconds. So far, so good. All I've used is time dilation, etc. Let's assume that when this person shined a light towards the mirror, my coordinate and that person's coordinate are the same. Okay? So we're the observer on the ground. We're the green person in the figure. Let's assume when the light beam was sent, both coordinates of the observer, which is us, and the person in the rocket were exactly the same. So x initial prime equals x final prime for the observer, but then for the person in the rocket, but then for us, x initial is 0 and x final is 40. So let's write that down too. Remember, the person on the rocket measures the two events in the same place. Okay. Now, according to the person on the rocket ship, our clocks run slow. So that means that if the person in the rocket measures this time between two events, we're going to measure, he's going to say, we're going to measure the time it takes to be less by gamma. And this is confusing. And the reason why is because clocks aren't synchronized. Okay? So, if rocket says delta t prime equals 30 seconds, then rocket observer says we will measure seconds. Furthermore, according to the observer on the rocket ship, the distance between points A and B is going to be 30 seconds times 0.8. And you can calculate different ways, either from that or from using this value and dividing by gamma. Okay? Now suppose there are two synchronized clocks at point A and point B on the platform. Okay? Suppose there's two synchronized clocks at point A and point B on the platform. That means t equals 0 for both clocks at point A and point B. These are on the platform. And the flash is sent towards the mirror. The stationary observer sees that the clock A reads 0 at A and 50 at point B when the ship passes. But the rocket says that they go from A to B in 18 seconds. Then what? According to the rocket ship, what is T sub B when the rocket ship is at A? That's the question. So, according to the person on the rocket ship, let me go back here. So this is what we observe. Two clocks. They read 0 here and 0. So we're A and B. The rocket ship is here. Okay, they both read the same. When the rocket gets over here, this clock reads 50, and this clock reads 50. But it takes, the person on the rocket says it only takes 18 seconds. The person on the rocket will agree that this will read 50 seconds. But what does this clock read when the rocket's over here? The person on the rocket wants to know, what does this read when he's over here?
Isn't it going to be like a little slower?
Well, it's going to be less, or it's going to be less than 50, right? If it takes this person 18 seconds to go from here to here, and this person agrees that this clock reads 50,
would it be 32?
then it's got to read 32. So the person on the rocket is saying it's got to read this thing's got to read 32 when I hit this. So this will read 32, and this will read, we don't know. I guess 0. These two are off by 32. Yeah, this will read 0, this will read 32. The rocket gets from here to here and now says, oh, now it reads 50. Now, if you calculate from the equation for the time delay, if you calculate this, 40 over c squared times v, you will also get 32 seconds. And the reason why you get all this complication is because that person in the rocket is going to say, your clocks are not synchronized. Okay? So the one thing that's hard to realize, to understand, is that that person is going to say that your clocks are not synchronized. That your clock, this clock is going to be ahead. And according to this person, if you're in this spaceship, all this stuff is moving to the left. Now, this takes some time for you to, this is a tough pill to swallow. I understand that. Okay? And it takes some time for it to sink in. Here's a picture showing you what things look like. Okay, this is from the stationary observer viewpoint. This is from the viewpoint of the person on the rocket. This is what they see. And those two clocks don't read the same. Those two clocks read different, according to the person in the rocket. But according to the stationary observer, both clocks read the same value at both events. These don't. That's the implication of synchronization. This is so hard to get used to. So, I'm giving you these ideas, and you might be intimidated, but you'll find that when we get to the kinematic stuff, the kinematic equations, those equations are much easier to work with. And you're going to spend most of your time working with the easier equations. I know this is hard, and it's a hard pill to swallow. But this hard stuff, you kind of need to understand, at least from a conceptual point of view, so that you can understand how we use the formal equations. The problem with the formal equations that we'll be focusing on, they hide all the physics. The physics is all here. Okay? Don't be too intimidated if it's hard to swallow. After looking at it a few times, you'll get it. Okay, I understand this is hard. And even on the tests are mainly going to focus on the formal equations we derive, the transformations. They'll make things easier. Questions? Or concerns? I know I don't have much time left. I kind of would like to just set this one up, and the reason why, I won't do the problem, I just want to set it up because you have a homework problem just like this. I want to set it up so you can get started on it, and then I can finish it off next time. Okay? This has to do with something called a twin paradox. So you have two 20-year-old twins, Speedo and Go Slow. Speedo goes to a star where gamma is equal to 3. He goes to a star going at a speed so that gamma is 3. Doesn't matter what the speed is for this example. And is 30 light years away. When Speedo comes back, he is 41 years old, and Goslow is 84 years old. Since the moving frames see the other clocks to be moving, since moving frames see clocks in other frames to be moving slow, who is actually the one who moved near the speed of light? I mean, normally you would say, oh, they're both younger than each other. How can that be? This is a twin paradox, and there's all kind of stuff written about it. Well, it turns out that Speedo is not always in an inertial frame. Why? Why is Speedo not always in an inertial frame?
Is it because he's traveling at the speed of light? He skips time, maybe?
What do you mean he skips time? He has to turn around, right? He accelerates, or she accelerates. Because there is an acceleration, you actually pick a frame now. And it turns out that Speedo, is actually the younger one, because Speedo ends up having to accelerate. Okay, there is an acceleration in this problem. There is a reference frame that's actually shows you can tell who's moving relative to the other one because you're accelerating. So it's Speedo the one that's moving. So there's a problem in the homework like this. And in order to do it, you need to ask the following questions. And then I'm going to stop because I think we're over time. You need to ask, first of all, I think this is homework 3. I think Jacob says homework problem 3. Is the twin paradox problem. In this particular case, two 10 students travel in separate spacecraft to Earth from, separate spacecraft to a planet 10 light years from the Earth. Person A travels at 0.866 C, point B travels at 0.6 C. You want to know what their ages are when they arrive. Okay, so this is similar to the twin paradox. In order for you to be able to do this, the first thing you need to know is, according to the Earth, you need to figure out the time it takes for A to reach the planet. Then you got to figure out, according to according to the Earth, how long does it take for B to get there? But since A is on the rocket, A ages slowly. So you use time dilation to figure out how much A aged. Same thing with B. Since B undergoes time dilation, you have to figure out how much B aged. You take the answer to the time it takes for B to get there divided by gamma. Then you got to ask, A needs to wait how many years for B to arrive? Okay. When A arrives on planet A, when A arrives on a planet, then A is in the same frame as the Earth. So you need to figure out how much he or she has to wait for B to arrive. And then you're able to calculate their age difference. Okay? So those questions you see in this slide should help you to do that problem. So this is one of the problems you can do now because it's really time dilation. The book doesn't say much about the twin paradox other than they say that one accelerates and then you can tell one is younger than the other. But there are textbooks which spend pages analyzing that problem in different ways. Okay, we're not going to do that because we don't have time. Okay. Well, thank you for staying a few minutes over. So our next meeting is on Friday. We're on Zoom this Friday, okay? Make sure you understand we're on Zoom Friday. And and it's at 2 o'clock. So we'll meet on Zoom on Friday. And we'll talk about it in lab then. In the meantime, if you have any questions, please email me. I know this is hard to swallow. I understand that. But you'll be okay in the end. My students survived last semester. They did okay. Okay, this first stuff is kind of intimidating, but you'll be okay. Questions? Concerns?
Nope.
No? Okay, so we will see you on Friday then. You guys take care.
I do have one question.
You have a question?
Yeah, so regarding the picking up the lab kits, do we actually need to do the whole through the Sierra app and getting the scanning code, whatever, just to get the kits?
Oh, to check in? Because you're just walking straight into the building, you don't have to do that.
Okay.
But when you come to lab, you're going to have to do that.
Okay.
And if you don't have a phone, we have sheets of paper you can fill out.
Okay.
Okay?
Guess I will go get that now.
All right, thank you. Yeah, they're open till 4, so. All right. Yeah, go pick up your lab kits either today or tomorrow. All right, we'll see you on Thursday. Thank you.